Webby, the streaming attendees, and saying it works or doesn't work, how we can improve it. We're also going to be recording these, so we had permission from Gabriel twisting his arm that we can record this so that we can share this later on through a YouTube video as well. We've done this before with the Climate Science Center webinar or seminar series that we had before. So with that, it's really a pleasure to introduce Gabriel. He's a world-renowned expert in remote sensing, especially looking at evapotranspiration. He's a USGS research scientist. He came to us here at NREL and the Climate Science Center in 2013, on loan from the USGS-EROS data center in Sioux Falls, South Dakota. So he's been really working with a number of students, faculty, and really providing some really exciting efforts. And from his title, you see that with the evapotranspiration work, we really try to bring what we've done, are capable of doing with remote sensing and looking at sort of water usage. So with that, I'll turn this over now to Gabriel, and we'll see if this technology works for us.
Thank you so much, Vince, for this kind introduction. My name is Gabriel Senay. I'm from originally way back from South Dakota, 14 years. Jeff and Dennis. Back in to come and be co-located. So I'm here staff of the Climate Science Center. What I'm going to talk about is using satellite data for crop water use mapping. The science is not new, but just we're taking advantage of the new technology with satellite sensors in mapping crop water use for drought monitoring purposes. EROS stands for Earth Resource Observation Science. It's located in South Dakota, Sioux Falls, South Dakota. And again, thanks for inviting me. So I'll give you an overview of what I'm working on. There's a bit of instruction on how to do this. So we share.
Yeah, sure. I think it's that thing with the.
It's already shared. So you think it's already shared? It's being online? Okay.
There's the man to talk to.
All right. So, glitches tend to happen. So, okay. Yeah, title slide. It's going to be smooth from now on. So these are my team and contributors. Most of them are in South Dakota. Again, as I said, I'm co-located here, but I work with a large group of team. So a lot of slides I'm going to show you is really supported by team members. We'll give a background and why we do the kind of modeling we do, remote sensing ET modeling, and I'm going to show you MODIS-based ET monitoring, and also Landsat-based some accuracy assessment, how we assess, the quality of our products, and also comparison with drought monitoring, remote sensing ET around. A little bit of background why we do this. The water census, the USGS program, has been monitoring water use every 5 years, based on state, county collected data. But now we're using remote sensing. Hopefully, we do this every year. And there's a USAID, a Farm and Early Warning project. This has been almost 30 years. There's also global monitoring interest, and the only way to do it is using satellites. These are the every 5-year compilations by USGS. And so what's the need for remote sensing ET? As of since 2000, only water withdrawal was being reported. Why? We didn't know, we couldn't figure out accurately the amount that's consumed. This is what's needed. So remote sensing is providing us now, at least attempting to give us what's being consumed. Basic principles, of course, it's the ET is the evapotranspiration, the combined impact of evaporation from the surface of the soil and leaves, and transpiration that goes absorbed by the roots and goes into the atmosphere. From hydrology point of view, it's one of the most difficult to estimate because when you look at precipitation and rainfall, precipitation discharge, they're in liquid form. We know how to measure them. ETs and gaseous still, which is invisible, it's always difficult to estimate directly. So only indirect measurements are applied. And why is it really that important? Well, ET as opposed to precipitation, we call it response variable. It's a response of a landscape. Whereas precipitation, the most important parameter variable for hydrology is a drought. It's a local scale. Precipitation is the most important. Without precipitation, there will be no ET, no runoff. So as a response variable, it reflects the integrated effect of energy, aerodynamics, soil moisture, and environmental stress conditions. So there are two components, and that's really what I'm going to talk about is based on these two components. There is a potential, which is amount of the available energy, and the aerodynamic forces, where the wind and relative humidity. And that's assuming what is not limiting. It's an optimum growth condition. The other components, how about the limitations? Limitation caused by moisture stress, vegetation condition type, and environmental stress like salinity. There have been a lot of efforts from literature to do this component. The potentiality starting from Penman in 1948. So I'm not going to really spend time on this. But remote sensing is supposed to give us the stress element. There are two scales in our work. One is what we call the field scale, where we want to know how much water is being used in an individual farmer field, like water rights issue including, or a basin scale. In that case, we don't know who is using the water, but we just want to know ET as part of the hydrological budget. We use Landsat at around 100 meter resolution for field scale. For a basin scale, we use MODIS, which is a 1 kilometer scale. So if we have a good method of estimating ET, all this would be, these other things would be also inferred from ET, especially explicit ET. What are the methods? There are two methods generally. There was a water budget and an energy budget principle. Water budget, what does it mean? We're just accounting for precipitation. That's a driver. So once we know how much comes in and how much goes out through a soil moisture accounting process. If you don't have good precipitation data, or we don't know how much irrigation, you have to go for energy balance. Today, I'm going to spend a lot more time on the use of the land surface temperature. Going back to that slide, the difference between the potentiality versus under stress condition. I want to show you this chart. This is from Arizona, and this is from a water balance point of view. So what you see in the green line is from January to December 2005. What you see in the green line is the potentiality, let's say using Penman mounting, so which is atmospheric demand. So based on energy, as you know, part of the year where energy is high, the potentiality is probably high. So that's the distribution of potentiality. So assuming that we know how to do this from previous literature. As you can see, the actuality would be much lower than the potentiality of the year at this time of the year. This is a monsoon period, and what you see in here is rainfall. So the rainfall is the stress condition from soil moisture. When there is no soil moisture stress, the potentiality and the actuality will be comparable. So what I'm going to show you today is how we do this actuality for coming up with the stress factor. Brief history, I'm not going to go through the details of this now. It's Penman. We came up with the combination equation, accounting for the net radiation, also aerodynamic forces, like relative humidity, the impact of relative humidity in evapotranspiration. Jensen, Marvin Jensen, I think retired, a lot of work in Colorado State University, also worked for ARS, who is one of the first one who used a coefficient in estimating irrigation water requirement. Of course, Rick Allen, famous ET scientist and professor, also came up with the reference with other colleagues with a reference ET concept of coming up with a potential ET. These are all potential, the one I showed you earlier. But the landscape is at a different levels of stress because lack of moisture or pests and diseases. So you have to account for the stress factors. So Allen and the FAO book, there is a stress factor for soils, the condition of the plants. So this is the potential, so you have to reduce it. The question is, how do you come up with these stress factors? So this requires the knowledge of crop types and the stage of the crop and moisture distribution. If you do all this, model this, then you will come up with stress factors, which is fine. It has been done in the past. But it means you need to know, for example, how much people are irrigating if it's an irrigated farm. So another approach, since the 1990s or even earlier, is the use of remotely sensitive. We can come up with these stress factors directly without a lot of assumptions. The land surface temperature is supposed to give us the combined factor, stress factor that comes from stress from soil moisture and also from plant conditions. So I will be spending a little bit of time how we come up with the stress factor. A lot of models are available. I'm not going to go through them. Even surface energy balance models. There's one of model. There's Psychrometry published in literature. And this is a simplified surface energy balance and operational aspect of it that we're going to talk a little bit more today. All models are wrong, but some are useful. Useful statement I like to keep because you compare your models to high quality data. You're not going to find a perfect relationship. So, but how much uncertainty can you tolerate? That depends on your objective. Where is the data source coming from? The land surface temperature comes from different satellites. If you go for Landsat, as I said, for field scale, you get about 100-meter resolution. If you go to just water budget, basin water budget, what you need is probably MODIS or Evapotranspiration, even goes about 10 kilometers. This is for the thermal data. But if you're driving your ET model with the precipitation, the most important input is precipitation. And then for the US, there is a daily, no an extra data 5 kilometers. For satellite-based NASA trims global 25 kilometers. But I'm going to be talking more about the land surface temperature approach. But before I go there, I just want to show you the water budget approach, which also we run. Important inputs precipitation. Let's say you get a daily map of precipitation at 5 kilometers. That's your important input. Then you need to know about the soil. That gives you the water holding capacity. If you do a simple bucket kind of model, you need to know whether it's clay soil, sandy soil. That gives you how much, is the buffering capacity of the soil. The other component is the atmospheric demand, the Penman-Montes equation. So under water unlimited condition. So we do this for the world now at EROS every day since 2001. So this is available as well. So assuming this is available and the soil stress factor comes from a simple water budget accounting, so the soil moisture is full, and then you're going to say this is close to 1. If it's dry, well, there is nothing to evapotranspire. The whole thing will become really actually to be 0. That's the basic principle. Of course, how do you get about the crop coefficient? Well, if you know the crop calendar, you can put that in. But you can, alternatively, you can use satellite-based NDVIs and normalize a different vegetation index. This is, for example, in Nebraska. As you would expect in the summer months, vegetation index is high, which means crop water use demand is high. So you can use NDVI as a surrogate to come up with, the crop coefficient. Out and I've done a lot of work to use this kind of thing. So the kind of productive data is what I showed you earlier. So you can estimate using your water budget, you can really come up with a good estimation of actuality. So what is the challenge? Why don't we keep on doing that? But the challenge is, in a water budget, you need to know how much is being applied. So you need to have good rainfall data, which is fine in the US. There are a lot of good stations. Generally, in the world, that's not really that reliable. You have to characterize the vegetation water use patterns, which is the one I showed you, the KC. And information on source should be also reliable. I think it's not a major problem in the US, except that irrigated, how much a farmer is irrigating would be very difficult to know. unless the farmer gives you that information. Which means he cannot really monitor the irrigation water use from water budget operationally. So these are really, also the impacts of pests and disease would be very difficult to quantify, incorporate in the model. So we use an energy balance approach, I showed earlier, as I will show a little bit later, that the land surface temperature is going to give us, you know what, all the stress factors from water, from agronomic practices or environmental stress, just one important parameter. And then, you know, the kind of product at the end, I will show you now how we do this. The kind of product we get is, this is, for example, annual total for the US. This is, you know, depths in millimeter. As you would expect, you know, higher ET and, you know, where there's a lot of rainfall, but also you'll find a little bit higher ET where there's irrigation Central Valley and Snake River region, stuff like that. So this is based on land surface temperature. So how does it work? Especially those of you who have not taken remote sensing, just one graphic on that. So the remote sensing, there is optical reflectance, like the vegetation index drive. You know, that's from something like this. Sense comes in, hits the surface, and reflects back, and there's a satellite sensor. There is another, the thermal, is the Earth as a function of its temperature. You know, this is the sun, 6,000 Kelvin, and this is its output distribution. Earth is much cooler, as you can see, around 303 Kelvin. Its energy distribution is very small. But even with that energy distribution spectrum, Earth still emits radiation, and that will be captured by the satellite sensor. So it's really, that's the one. So how much is being emitted as a function of its temperature? What we're saying here is that temperature carries a lot of information for us. So this is an example, a close-up of, this is the land surface temperature from Landsat data. This is the scale. These are cooler surfaces, and the warmer colors are dry places. So where there is a center pivot vegetation, it's much cooler. The difference in temperature could be as high as, you can see here, 40 degrees centigrade. Whether an area is watered in soil moisture or in well-watered vegetation versus no vegetation, could be huge temperature difference. So what are we saying here? Emitted radiation from Earth is a function of its temperature, as I said, but evaporative cooling lowers the surface temperature. So when a plant evapotranspires, because evapotranspiration takes a lot of energy, so it cools the surface. All right, so this is a true false color of composite of the previous image. So how do we model this? Very simplified operationally. Well, we use a land surface temperature that we get from satellite, combined with some air temperature parameterization. What we are saying is we will get an ET fraction that varies from 0 to 1 on a pixel by pixel basis. And then you multiply that ET fraction by a potential ET from Penman-Montes under ideal condition. And then we get ET estimation. Very simple, operationally doable. Does it work? Seems to work compared to other models, but at least for us, for two purposes. Drought monitoring, we have a lot of confidence in it. For water budget analysis, it's decent, it's good, it's comparable to other models. I'll show you something. Again, as I said earlier, the basic principle, if the land surface is bare and dry, a lot of the net radiation that come from the sun will be absorbed by the surface and it heats it up. But if it's well watered, it's evapotranspiring. So the heat will be removed by the water vapor. So the temperature cools down. That's the basic principle. That temperature difference up to 40 degrees Fahrenheit is for us, it's a stress. There's no time to go through all these equations, but the net radiation is can be sent out into latent heat flux, which is the amount used for evapotranspiration, amount to heat the air, and the one that goes into the ground. Standard energy balance models first calculate the sensible heat flux because directly measuring is harder, and some assumptions also this can be estimated. And as a residual, you can come up with latent heat flux. That's full energy balance models. We don't do it that way. For operational purposes, we estimate ET directly using ET fraction. How do we get the ET fraction? Well, this is what's being measured from satellite, and this is derived from some factor using air temperature, and this is also predefined. I'll show you a little bit on that. So at the end, the model looks like this. Well, you get the satellite data, land surface temperature on a given pixel. You combine it with other factors we can predetermine or just get from property of the air. And this has to be estimated independently using weather data. As I said, global data simulation systems, we have this data for the globe. So what's new about this method? Especially Tom is here, we have a lot of questions. What we avoided, if you're familiar with metric and SSEBop, in this method, what we avoided the need for using the hot and dry reference. What we just need to just estimate the cold reference boundary condition. So at the end, the ET fraction would be just simply the difference between the surface temperature and our cold reference and some constant. I'll talk about this. So I think this is the first time I'm putting together a manuscript to explain this method using the psychrometry approach. So some of you might be familiar with psychrometry for relative humidity measurement. Okay, I see some noise. So in psychrometry, you have got two thermometers. There is what you call the dry bulb that measures ambient air temperature, and a wet bulb that's weighted by a cotton lid. So the difference between the two will give you the measure of relative humidity. When the air is dry, the difference will be huge. So that's the principle in psychrometry. I even have my own psychrometer. I'm going to pass it around. So there are two thermometers in here, and one is weighted bulb, and the other is dry. So you just weight it, and what you do is just you swirl it for about a minute. I just bought it online. And then after a minute, you will see that a drop in temperature. You can pass it around. So that difference in temperature is a measure of the relative humidity, the vapor pressure. So now, how am I going to translate this into a satellite? Let's see. I succeeded. Again, it's the first time I'm talking about this. So you have got a wet bulb and a dry bulb. And what you need is the psychrometric constant, the property of the air, and these three equations really depends on your location. At the end, it boils down to just the pressure of atmospheric pressure. That's constant. So we can measure the dry bulb, the wet bulb, and this is a function of the temperature of the air, the saturated vapor pressure. So we can estimate that. Okay. So how about this? Vapor pressure versus ET calculations. Well, what I'm saying is I can formulate using satellite data actual ET estimation using this equation. You can see this is the potentiality. So now I'm deducting a factor from the potentiality, and this is a stress factor. This stress factor is temperature measured by satellite minus a cold reference. In the psychrometer, this is the difference between the dry bulb minus the wet bulb. So now the question, okay, this I get from the satellite, the surface temperature. Where do I get this? The cold reference. The cold reference could come from, a well-watered vegetation. Just like the wet bulb in here is wrapped with cotton. So that's, but in psychrometry, you need one psychrometer for this room. So you need another psychrometer in another room for outside, right? How are you going to get in satellite? Well, satellites, you can see them as millions of thermometers because every pixel you get a measure. So the difference is psychrometer measures the air, the satellites measure the surface. All right. So in summary, without going just too much, a large temperature difference in psychrometry gives you, as a function of a dry air, a low relative humidity sense, low vapor pressure. Same thing here, large temperature difference between the surface temperature, which is a drier soil, and the cold reference, which is a well-vegetated area, gives you a lower soil moisture. If it's lower soil moisture, the plant cannot evapotranspire. If it doesn't evapotranspire, it means it's not getting the evaporative cooling, so it heats up. All right. So now I'm going to show a true sample from a satellite data. So this is a transect going in this Wilcox irrigation basin, part of southeast Colorado River Basin. So we're going to go through this transect and see how it looks like. As I said earlier, this is land surface temperature. These are thermometers now. Surface thermometers, these are cooler surfaces, blue, and warmer surface. So what we're saying in here is surface temperature minus cold reference. Okay. So in that transect, this is point A. You go through the mountain in here, and the valley is where irrigated fields are located, and so you back up to the mountain. And now, what you see in the temperature space, there's a distance from here to here. So let's look at this temperature first. This is the land surface temperature that's comes from satellite, Landsat. As you can see in here, it's kind of a noisy data because there's some information, high variability. So it's high temperature here in the desert, and then drops down. Especially it drops down here, and these are central pivot irrigated fields because they evaporated cooling. So now, what is this line? This line is my cold reference point. That comes from pretty much from the air temperature. Well, there's some calibration to use air temperature as a surrogate for the coldest vegetation. But that's how the principle works. Yeah, you following me? Okay. So now, how this translates into ET and other vegetation indices, which is the same area. What I'm showing you here is let's look at if really makes common sense. What you see in here is the vegetation index. High vegetation index, higher ET, right? So these are, irrigated areas in here where vegetation index is high, pretty much ET is high, as you would expect. And that's because of really the ET fraction. In terms of potential ET, this is a small area. The potential ET doesn't change that much at the local, scale. As you can see in here, it hardly changes. Stays around 11 millimeters per day. But the actual ET varies highly as a function of moisture, as a function of the land surface temperature. I said earlier, potential ET doesn't vary that much. That's true at a local scale. Potential ET varies seasonally, and also at a larger temporal spatial scale. So what you see in here is southern Colorado and northern Colorado River Basin. The north, this is the mountain area that's cooler, and lower temperature, lower ET. So there's about 40% difference. You can see the seasonality of our ET comes from the potential ET using Panama MODIS, but the spatial and temporal variability comes from the satellite. All right. So I think we have done a lot of the background psychrometry, satellite psychrometry. Now I'll show you, graphics, how the data looks like. So these are the data sources, for that goes into the model, as I said earlier. This is an example of a MODIS satellite, which is its geometrical configuration. And we use a thermal band, and NASA calculates the land surface temperature for us. Actually, we download the land surface temperature. The global product would be like something like this. This is an 8-day product. The Penman-Montes equation we saw, this comes from the 6-hourly weather data, comes from NOAA, for radiation temperature winds. So this is our potential, comes from there. And we have a website where we post the products, and we have the US and global products. This is the kind of product I showed you earlier based on that principle. But the anomaly is more useful for drought monitoring. So the absolute magnitude is good for water budget studies and irrigation water estimation, but the anomalies are for droughts. For example, this is the previous year. So what you see in here is average condition, but above average in green and warmer curves in below average conditions. And this is the previous year. And this is 2014, and there was just a drought in Texas and western US shows up. And these are the different years, and you can see the 2012 drought, and again 2011 drought in Texas and Oklahoma. And if you go back, MODIS started in 2000, so a lot of our analysis starts in 2000 using MODIS data. But these data are posted on our USGS job portal and available for download. Also globally, we do monitor different countries as part of USAID projects in countries where US is interested. And this is a global product. These are anomalies, 2015, including the US. And these are seasonal, March to October. 14, 13, of course, drought in the US, but also drought in Europe, 2012. And 2003, there was 2010. 2003, there was a huge drought in Europe, now it's picked up. So, and the historical values and data are also downloadable from this website. So now I just want to show you some more using Landsat. What's the difference between Landsat and MODIS? MODIS, spatial resolution. MODIS is 1 kilometer thermal data. This is about 100 meters. But at this scale, they're comparable. Higher ET in irrigated areas and mountain forests. The difference comes in when you zoom in. So when you zoom in the small location here, you can see the center pivots in Landsat, where this is pretty much smooth. So if you are interested in just average value over this area, you can average this, you should get comparable results. But if you want to do just monitor a farmer's water use, you have to use Landsat. So it's really depending on your objective. Of course, you zoom into irrigated areas, center pivots, and big. So what I'm saying, relatively using satellite data, you can estimate, monitor water use fairly accurately, especially when water use is high, like irrigated areas. Our error will be much higher, like in drier areas. Same here, measure this in northern Colorado. Again, in Landsat, it comes every 16 days. If you're lucky with 2 satellites every day, cloud is a problem, but still we managed to get some monthly estimates. We have more confidence on seasonal estimates compared to a daily or monthly estimates. So how does this model perform? And of course, you can start with visual and flux towers and water balance. It's running all the time. So this is Central Valley in the US, Snake River. And it takes us high plains. You can see irrigated areas just showing up. This is again based on MODIS. Our collaborators in Arizona Water Science Center were interested to use this method. So they did some field investigation, and what you're seeing here is the ET estimates come from on alfalfa as you'd expect. But of course, fallow lines will have no ET pretty much. They our model estimates, but averaged by different crop types, comparable results. And we did some more years of data. Just want to show you in here, 2012 was a very dry year compared to these other years. As you can see, the background is a lower ET as you would expect. But irrigated fields actually, they're much darker, which is higher ET. So which means the potential demand was much higher in dry areas. So in drier years, irrigated fields would have to water more. That's common sense, but the satellite data just gives you that information. And we're doing now historical ET and Palo Verde. These are every 10 years, but we have done this every year. And you can see there was a following program in the later years, 2010. There was an agreement with the Los Angeles Water District. So water could go to support the city of Los Angeles. So satellite data just pretty much can see that. And you can see that for the same Palo Verde Irrigation District, they were doing the following program, peak following program, water use was much lower. And we use flux towers to compare our model. Again, this is our air temperature, cold pixel, but you can see the land surface temperature going up and down. And this is a monthly comparison. It's pretty good. Again, there's a good correlation with flux tower data, different parts of the country. We think the model performs around plus or minus 80% on a monthly time scale. And it will be better at the seasonal time scale. Comparison with MODIS 16, the NASA product, it's a water balance approach. This is a gridded flux net from Max Planck in the in Germany. This is published. Again, this is our estimate. I think we have captured the special, very special in irrigated areas much better. Special for graduate students, how you use this also for water budget studies. I just got a couple of slides to show you. So this is the whole Ohio River Basin. So this is precipitation data. And this is our ET estimate. The cities and like this Columbus, Ohio, that went to school had lower ET, but other areas have much higher ET. Now, can you do a water budget? So this is for the whole basin. So what you see in here is rainfall distribution in the bar graphs and actual ET from the model. And what you see in here is a runoff for the whole basin. As you can see, there is a lot of rainfall. Rainfall in the whole basin is generally high. But you can see the runoff. There is a much lower runoff when rainfall is still high. But that could be explained by a much higher ET during the summer months. So ET helps you really understand why a basin behaves in a certain way. Just a few more slides to show you how this compares with the drought monitor. This is the latest drought monitor in the US, August 16, and this is our seasonal estimate of drought anomaly from April to August. Generally, it captures, where the drought epicenters are, and this is the whole season. But when you look at the monthly, month by month, probably August will show a much higher, maybe drought incidence like what's in here. So that is where the bigger difference is. When you zoom into different years, this is actually, Dennis and Bob, they asked and they wanted to see how our ET anomaly compares to the drought monitor. So they did a really creative work of, drought monitor is a weekly product, but they created a 3-month product. As you can see, the drought monitor doesn't show when it's above normal, they only show when it's below normal. So what you can see in here is a below normal condition, and the same thing in here. The difference in here is this is automated, pretty much nobody touches it. Data comes in, the algorithm spits it out. And this involves a lot of people. There's some consensus, there's some subjectivity. So the hope is, this could be incorporated and improve this program. It's another 2012, again, widespread drought, a couple of high boats, 2013, 2014. So in summary, the model is a physically based model. Like any other model, there's some empirical parameterization. But generally, it's physics-based. Most of the parameters are derived from property of the air or surface. The model accuracy is, I think, reasonable, comparable to other models as well, but operationally is much simpler. Again, we use this to monitor drought anomalies across the world at 1 square kilometer. But with some calibration and making sure the absolute magnitude is correct, can be used for crop water use volumes. So that's where we have to be very careful. Anomaly calculation is, we have confidence. Any bias we put in the model, it drops out when you do the anomaly calculation. But then the bias will remain unless you remove them through some calibration or validation. That's all I have, and I'll be very happy to take any questions. Thanks. That was great. Any questions from here? Don't forget my psychrometry.
Really interesting stuff. So I'm interested to know about, you mentioned very briefly that there's some data available for historic back in 1984. Was that for that one particular region, or is that?
1984 would be for Landsat.
Yeah.
Right. MODIS would be 2000.
Okay.
Yeah.
All right.
Yeah,
And so is this data available going back all the way to 1984, these estimates of evapotranspiration?
No. The ET from Landsat would be on a demand basis. Yeah. But we are working with Earth Engine, Google Earth Engine. We try to find this going back to 84. We're still working on it. But the MODIS one, since 2000, is available for download. It's 1 kilometer. Yes.
Is there a way to forecast for future, like future months or years?
Yeah. Good question. Satellite data, as you know, it's observed data, but through modeling, you can forecast. Our model is a combination of satellite data that gives a stress factor now. That's what it does. But the potentiality can be forecast. The atmospheric demand can be forecast. So with some understanding of your current demand now, you know, it's possible to forecast, at least create some kind of ensemble scenario.
And one of the things that we're doing in the North Central Climate Science Center, in collaboration with Bill Parton, Ellen has been involved, Linsky, is that we're actually both cross-calibration evaluation of contemporary the last 15 years.
All right, well, thanks.
Over this domain, but then because you have an ecosystem-based model, if it calibrates to the remote sensing data that Gabriel has, then you can project forward with different scenarios, you know, at a coarser resolution because the downscale climatology that we have is in the 4-kilometer resolution. But at least then you could actually look at different scenarios of future projections of ET. Yes.
Are there good satellite data that can be used to validate the models in areas where you don't have police towers and a lot of on-the-ground observation?
Yeah, that's a challenge. You know, flex towers. That's why most of our calibration publication comes from US data. But when you get out of the US or Europe, water balance approach is the best, which is you look at the whole basin, and then you have to do it on annual time scale, because that's where water balance really makes sense. But that's an approach we have been doing actually, like in the Nile Basin and stuff like that. So you do, okay, the rainfall is this, and this is a discharge, but it means you have to get the discharge measurement at the basin outlet. So if you have the rainfall and discharge, the difference you think, storage change being little negligible, the difference should be ET. And then we compare that to our ET model at the basin scale. So
at very large scales, you can always use GRACE data.
Sure.
And some of the work that Gabriel's actually developing is actually looking at the basin-wide GRACE estimates. Unfortunately, the SWAP, I think it's the SWAP that the high resolution sensor SMAP failed. And so there's a new mission that's being considered. I think in the Dakota survey, soil moisture aspects is still a very critical system variable that we're trying to get to capture. So I think the next mission probably is in 2020, 2025 range. So in your lifetime, you can actually get the high resolution remote sensing validation that you might want.
Yes.
So, Gabriel, when you were looking at the transect and you were using that example, and you have that lower bar that the coal sort of, how empirical is that, and subject to data, and then extrapolated to a region, or I guess it's that lower curve.
Yeah.
Does that fit to your data?
Yeah, so that's a very important, it's a good question, very important parameter. So now we're using air temperature, but we know that air temperature, land surface temperature, they don't really necessarily, because surface skin temperature, air temperature is measured at 2 meters. Roughly. But what we do is, whatever bias there is, we correct that for bias using a calibration coefficient. So which means wherever there is a high vegetation, densely vegetated, like NDVI greater than 0.7, let's say, that's where we assume the two should be compatible. The surface and the air should be close. Tom, you can comment on that. So but with that assumption, we remove the bias using that coefficient. And hopefully you have got those vegetated areas well distributed throughout the US, so that that calibration keeps on being checked. But that could bring really a big problem if you are really a large plot of only vegetation.
So in a way, you're still using cold pixels.
Yeah, we do. We do. Yeah. You got to stay to the reality, because that the assumption is the same that SSEBop and metric use the quote well vegetated surface is at maximum ET. But the only thing we bring is just bringing air temperature pretty much to interpolate spatial, so that you don't have to pick cold pixel everywhere.
You mentioned this Google project. Why don't you just give a minutes on what that is?
Yeah, the Earth Engine, I think anybody can get account with Google Earth Engine. They have their own pretty much GIS. So as long as you're willing, there's data. I mean, they have downloaded Landsat data, MODIS, the weather data is there. So you can implement your code in Earth Engine environment, and it's so fast to do the whole globe in DBI processing that would take days and days. In Earth Engine, it could be done in 2 minutes. Because it's cloud computing, they have distributed, they send every pixel to different computers, whatever, I don't know how it works. But you send, you submit, and the result comes back within a minute. There's in millions of other thousands of computers they distribute it. So that's pretty much how Earth Engine works. So we have an account as an experiment, we are working with them, and we are implementing our code in Earth Engine in Sioux Falls, South Dakota. So we're getting good results, actually. I didn't show it, but we have Landsat ET fraction for the whole US. So that the idea is to go back and start processing from 1984. That's the only way to cover US operational in Landsat. Just takes too much time on a personal computer.
So let me just ask the crowd, are there developed students in here? Well, you should, with your other colleagues in develop, actually share this sort of information about the Google platform. Also, sort of opportunities working with Gabriel on ET products for class products and things. I know that you guys are constantly looking for those, but I think actually, well, anyway, that's enough as an advertisement for.
I know I've been talking to Amanda and the group. Amanda's interested in ET, right? Yeah. Yeah. I think it's a great opportunity to jump into you can code in Python, and also they have their own API, but Python can be also implemented in Java and Python and Earth Engine.
So just to play devil's advocate, somebody said I can just use NDVI.
Right.
Yeah. Why do I need all this? Where do you see that? Because you have the graphic that kind of almost showed that one-to-one map.
Sure.
Where do you get this physically based temperature differences where you're not getting that? And it's maybe it's an earlier warning or a different signal. So where is it different than NDVI?
Yeah, no, that's a good question. Now, as you know, people work with NDVI. NDVI has got a saturation problem. That's one thing. In terms of sensitivity for drought, NDVI responds less because the memory of vegetation is based on color, right? So plants could be stressed, but plants could still look great. It doesn't mean they are not stressed. When plants are stressed, their physiological activity will reduce, yield will reduce. So that's one thing. It is not only from plant surface, it also happens on moist surfaces. And a well-watered moist surface, especially early in the irrigation season, could be evapotranspiring at higher rate. But NDVI is going to show you there's no heat. So that's really advanced. Otherwise, NDVI is also a good substitute, to estimate ET. Yeah. Yes.
Who would be the end user for this kind of model products?
So drought monitoring is one thing, for the globe, USAID is a bigger user because we want to detect food shortage, food security issues. Same thing in the US, drought is an issue. Farmers, rangeland, insurance people, crop insurance, stuff like that. Water budget, water use, this would be like Bureau of Reclamation. For example, they need to allocate water to irrigation districts. So which means you need to know how much water is being used in a given irrigation district. So even if you know what happened last year, it will help you plan this year. So really people who allocate water, who monitor crop production. So there are a lot of users. Anything that's tied to yield, crop, water. Yeah. Yes.
With those drought monitoring products, do you find that drought has a memory that if you have a really droughty year that you can't totally recover the next year, that it takes a while to recover from drought? What do you observe?
No, it's very true. Actually, in areas where we monitor the world as well, it's not a one-year drought that really hurts the farmers or the pastoralists. It's usually like a 2-3 year drought. Whether you can model that memory, I don't know. But when it happens, consecutive droughts hurt the farmers. But whether you can model that, I don't know. These are climatologists can answer this. But the impact of consecutive droughts is much higher than a single year drought because it's tied to whether you have food reserve and stuff storage. Yeah.
Thanks, Gabriel. This has been a great start for our setup. As a reminder, this happens every Friday. Our next speaker is Jeffrey Herrick from USDA. He's a rangeland scientist. He's going to talk about indicators and some of the efforts he's doing both domestically and internationally of looking at sort of rangeland management with these different products that he has. Gabriel is just down the hall. If you want to communicate with them later with questions or different ideas, he's just here in the Climate Science Center in room 309.
Yes. Thanks again.
Okay, thank you.
Do you want to get some, how do I get up? Stop sharing, I guess.